All right, welcome everybody. Let's get started. It's my pleasure to welcome you to Advanced Deep Learning for Physics. As I hope you're all aware in the right room here. Today I want to start fairly easy, giving you an overview of what the course will contain, a bit of the organization for the whole semester following now, and also get started with some of the first actual content. And let's get started. So we're dealing with deep learning methods, or AI as you would call it. So we've been doing this course for a while now, and especially a few years ago, it used to be, well, I thought it made a lot of sense to really motivate this from the start, why this combination should be looked at. By now I think it's becoming more and more obvious that there's something interesting here. If all the buzz about ChatGPT and co, the Turing Awards and the Nobel Prizes are any indication, there's some useful technology here. So by now I think it's relatively clear. Nonetheless, I think we're facing a few specific challenges in this combination of physics simulations and all this AI technologies, which justify looking at just this combination, and that's what we focus on. So in a way, what I also want to build all the content on are classical simulations, and these are around for a long time, much longer than neural networks and deep learning, and they've been extremely successful. So just to mention a few examples here from plasma physics, some neat examples next door, right? Combustion engines, aerodynamics from planes over cars, quite relevant here in the area, to blood flow in our bodies. There are many applications and many success stories where simulations have been really very, very powerful. And right now we have this relatively new AI whole field by now of AI. And the big question is now how to best combine these. So also my big standpoint here that I'll reiterate many times probably in the next coming weeks is we don't want to throw these simulations away. We want to build on them and just combine it with all the techniques from the deep learning field, in a way aim for best of both worlds combination here. Right, so we want to join forces. We don't want to replace simulations. And also I think simulations will benefit massively from the AI techniques. So one nice way to think about this is from this book by Daniel Kahneman, Thinking Fast and Slow. Has anyone read this? Excellent, right? So it's a nice read. I can recommend it anyway. Unfortunately, Kahneman passed away last year, I believe. But it's really a great book that has nothing to do at all with neural networks, but he explains how our brains work in terms of two systems. So he says, he has a whole bunch of experiments, and his experiments indicate that we can separate it into a very fast, intuitive process, like what you're doing now, right? You're looking at me. You don't have to think much. You can see and understand what I'm saying. Right? It's very fast. In contrast to a slow and analytic process, if you go home for the homework and start to work on the assignments, right, you probably need to sit down and think about it and work it out step by step. So these are really two systems, and to make it intuitive, he calls them system 1 and 2. And he does not talk about numerical simulations at all, but I think it's a nice viewpoint. So in a way, we can think of these classical numerical simulations in terms of a careful and analytic stepping process, a basis that is augmented by these neural networks, providing a more intuitive, ideally also very fast process that improves the result. And we don't need to think of these in terms of just single steps going forward, but ideally these really work together hand in hand over a whole series of steps. It's also something that's going to come up quite a few times. For example, if you look at time-dependent phenomena. So it could be a time evolution where a solver produces some basis along which we want to work, and then the neural network on top gives us an improvement that takes this simulated output as an input to work on. Also a bit in terms of the general motivation, it's worth looking at how scientific, or kind of reminding ourselves how scientific discoveries are made. And the traditional, or one way to traditionally divide the different pillars, if you want, of all these methods is, or the very traditional one was just theory and experiment, right? Classic Newton or so. We make observations of the real world, think about it, and then come up with a nice theory. By now, computations have really spread probably almost everywhere in scientific disciplines. And working with data, what you would now call machine learning, is actually not very new. It's also good to remind ourselves, right? In a way, all these experiments collect data. We process the data to improve our understanding of nature. And there are very good examples like Kepler's orbits, for example. We gathered a lot of data, how all the planets move, to come up with a theory. Darcy's law or PCA is also a good example, a more recent one. And in this context, working with data, however, I still want to argue that these deep learning techniques really give us a different way of working with data, especially if it's a lot of data. So the classical way works nicely if we as humans can understand the data, and if you look around by now, the amounts of data that simulations or other environments like the internet or so can produce are just gigantic and way too large to be manually processed. And here, automatically finding the key modes or components that help us, that we're interested in, is really important. Yeah. Also good to mention here, right? Ideally, we think of research in terms of this brilliant insight. Actually, probably Einstein's theory of relativity is probably a good example there, right? He had this brilliant idea, and then on that, there's by now many fields that worked on this. That's not, unfortunately, how it works in many other cases. Rather, people have ideas, try things that work a bit, but not as expected. Then other people take it up, refine it, and it's a long process with many steps in between, often very small steps. Navier-Stokes is actually a good example. There also took a while to figure this out based on these continuous formulations back in the days. So despite being much harder and not this ideal way of doing it, it's nonetheless one that is often applicable and also leads to very interesting successes. Worth mentioning here that traditional numerical methods probably follow the same path, right? So if you think about just traditional finite difference solvers and so on, they came up around World War II. They initially were frowned upon because, right, you don't have a nice analytic expression, but it's something approximate. You have errors. So it did not have an easy standing in the beginning compared to the nice pure math solutions. By now we know it's extremely useful if done right. And we understand the errors, we can get them down. So it's also been quite a stony path, if you want. And deep learning also followed the same kind. I'm sure you've heard the stories from the 70s, right, the different waves of neural networks coming up and basically almost disappearing again because it didn't work. Now it's finally working, but it wasn't clear 50 years ago when people started to look into it. And also, an important point to make here in the context of numerical methods is that for physics simulations, for the classical ones, we now have the proofs. We know how to choose certain parameters, how to have error bounds on certain methods. Not even all, but on quite a few. So we have a really good understanding of these methods. For deep learning methods and the combinations, that's not there. We typically don't have error bounds for neural networks and for the general training process. But I would argue that's not a reason not to look into it. People are working on this. I'm sure it's going to improve a lot. And nonetheless, it's an extremely powerful method. So I strongly want to argue it's worth looking at right now, despite the theory lagging behind. And also, we're in computer science. We will actually not deal a lot with proofs and theoretical results, but focus on the application. In terms of categorizing the different topics that we look at in this lecture, it's about bringing these physical simulations and AI techniques together. And here, this is a schematic to illustrate that a bit. We have our physical simulations. What's important to distinguish from a simulation perspective are forward versus inverse solves. Right, I'm sure you all know forward, where we set up something, initial state or so, and then we evolve in time to basically predict the future, right? How it's going to evolve. Are inverse problems familiar to everyone? Right. Here the question is basically the inverse, right? So the other way around. We're dealing with a simulation, but we're not just interested in how does it behave in the future, but we, for example, want to find a parameter of the system. That can be either the geometry, that could be something like the diffusion coefficient, or in the most general case, can be any parameter of the system we're studying. But it's basically we're optimizing for some quantity that is not just the future state, and potentially this involves many simulations. So this is really kind of an outer optimization loop. And if you're unlucky, can involve a huge number of simulations. So typically these are orders of magnitude more expensive than the forward simulations. But for practical applications, probably, actually most of them are inverse problems. So if you think about something like car design, where flows would be interesting, by now it's done, right? The designer makes a model, puts it in a virtual real wind tunnel to check the aerodynamics. What they're probably interested in is the drag reduction or feedback about how certain parts of the shape influence the flow. They basically to go in and manually fix this up. What would be ideal is if we could say, well, look, I'm designing a new rear view mirror, minimize the drag for that, or some other properties. So automatically change the parameters of the system to give the solution, and that's what's these kind of optimizations are what's summarized under inverse problems. Yes, there was a question. Exactly, very good example. So for people watching online, the question was, if I have something like an egg or ball rolling down a mountain, right? The forward simulation would be I put it somewhere and then see where it goes. The inverse problem would be, how do I need to change the slope of the mountain so that it lands in a specific spot, or maybe avoids an obstacle or so, right? If I can change the landscape. This typically is quite inverse and could involve even more degrees of freedom than the forward problem. Right? If you think about the mountain, very good example, I could parameterize the mountain in terms of a whole landscape, right? I could have thousands of degrees of freedom to specify the mountain, just to put my egg or ball in a specific spot down the hill. So it's potentially actually also a wide range, but very relevant for practical settings. And also, as a look ahead, they can be treated very similarly. So it's actually typically, once you have a forward simulation, it's not too much work, especially in the deep learning context, to turn it into an inverse solve. That is actually one of the nice benefits also. Yeah, so this is actually purely the simulation side. So now how do we bring in the learning? I want to distinguish three really different approaches here. One is a purely data-driven one, basically just taking data from simulations or physical systems. Right? Ideally, this could also be an experiment, although that's more challenging in practice. But really just taking the data and then, in a way, using typical deep learning methods. A nicer way to do it is to at least change the loss. If we know something about the physical systems, we can actually, these loss functions, which I'm sure you're all aware of in some form, right? Typically, we have at least an L2 loss or something for regular training. We could change this into something that takes some of our understanding of the system into account and puts some priors or some more directions on what is being learned. Right? That is one other way to do it. Still, right, it kind of only puts it in the loss. You imagine, right? Can we do even better? That's what's summarized here as hybrid. That really aims for having a numerical simulator that is some discrete computer-based version of our physical model and tightly couples it with a neural network. So that's potentially actually a large ground, how to combine the different parts. But this, in a way, provides the closest integration of the two. You really have a solver that works hand in hand with the neural network to produce a solution. And also these three different ways, actually the first one not so much, but especially the last one is probably taking the largest amount of time also within the next weeks. Although also thinking about it, we get back to these other variants regularly because they're in a way simpler to do, and also, for example, it's actually still a good starting point. Yeah, I directly want to give a few examples of these three scenarios. So one is, these also should serve a bit as starting points if anyone wants to run some experiments. So you find some links here which you could check out afterwards if you're interested. The first example for this purely data-based approach is a very classic one. So there are these RANS flows. Right? So actually, we use fluid examples quite a bit as a dense PDE and a non-trivial one. So I think it's a good example. And here, this is also one case that's probably in industry the most widely used one for Navier-Stokes. It's a time-averaged solution of something like airflow around the body. So you don't want to resolve at every point in time how the airflow might change, but you're just interested in the long-term average. And it's good for something like airfoils, and I hope you can see it a bit. So there's a tiny airfoil here in these pictures. So that's the input to a neural network, actually. This specifies with this cutout region, basically the shape of an airfoil, and then also the direction from where the wind comes, or where it's moving, basically. And then the typical question is how does this shape now do in the flow? What kind of lift and drag, and what kind of vortex shedding does it produce? And this is being solved many times in industry. So we also actually just tried solving, fully replacing this RANS solver with a neural network. And it works. Okay, it's not too surprising if you choose a good architecture. In this case, it's a UNet, indicated here a bit by this up and down process. I hope that's familiar for some of you. You can actually get the answers, in this case shown here in small insets on the right side. And if you give it enough data and enough parameters for the network, it does a pretty good job. You can tune this and refine it in all kinds of ways, but this basically just takes the data from a RANS solver and just replaces this solve with the neural network. And typically, if your network is not too huge, actually these solves are by now can be done relatively efficiently, but typically a network will do a good job and be faster. Although not depending on how you solve this, probably not gigantic by gigantic amounts, but you can see speedups here. So that's the first use case. This actually by now I just learned talking to some people from simulation software companies is by now also integrated in a few of the simulation packages that you can directly, based on your tests, train a model that kind of recreates solves that you have to get simulations faster. But that's really only taking the data and then producing variants of that, typically some form of interpolation, can be a new condition, so it's still useful from the data is that it has seen on, say, a new or changed geometry. For the second example, these loss terms that I mentioned, one good example is a very classic paper from 2018, I believe, that puts a physics constraint into the loss. You can actually see this as a form of unsupervised training, because in a way, you're not pre-computing every single example, as with the previous case, right? With this previous airfoil example, you basically run your RANS solver, right? Hundreds of thousands of times to produce a big data set. And here for these loss terms, seemingly you don't need any training data. So what in this example was done was to, in a way, minimize divergence. So gradient dot a velocity field, in this case, actually a flow field produced by a neural network, right? This differential operator measures the amount of compression or expansion of some flow field, of some motion. And if we compute this, so this is relatively easy to compute. For some of you, right, a gradient is just a spatial derivative, 2D x and y. The dot product we added up over, say, a computational cell. Then we have a measure for how much motion, encoded in this case by this f, so this needs to be a corresponding vector, compresses or expands. And if that is minimized, if that's 0, that means that this motion here from the f does not expand or shrink things It's divergence-free. It conserves volume. So that's an important property for many physical systems, also for typical motions like air. So that's actually a neat constraint. And you can basically train a network, putting this at the output, telling it to produce solutions that do not compress or shrink or grow things. And seemingly, you don't need data then, because you just run the network, let it produce something, and then it gets feedback about how wrong was it, how much does it compress or expand. Effectively, this of course does produce data for training. It's just computed on the fly. The network needs a learning signal. We want to optimize something. We need a direction. This is just computed, or it's so cheap that it can be computed on the output of a neural network, and you can train with this. So I'm actually not a big fan of this unsupervised label. It effectively means more that we compute the data or the training signal on the fly. Nonetheless, this can be useful. We don't need to pre-compute. We can train generating what to train with on the fly while running the network. Yeah, and this was actually used in this classic paper. You can also find it on GitHub by now to learn in 3D flows around obstacles like different shapes. If you set it up correctly, again, this does work quite nicely. And the nice component about the nice aspect of having these loss functions potentially is if your data doesn't cover all of the variations, or maybe even misses some aspects of the physical behavior that you want, like in this case, not losing any volume. While training, you can potentially, in this case, you just need to be lucky, but you can hit these cases and still learn from it. And by now, there are actually also methods that try to steer this a bit more to directly go for areas where the network does not do so well. So that's potentially also possible in these settings. Yeah. To come to the third case, is more even tighter integration, these hybrid solvers, as you could call them. Here's another example from one of our own papers. So basically, in this case, you really have a normal solver that does a classic solve with numerical methods. But in this case, this is not the final answer. So we basically know, or you can set this up such that the initial solve is not producing the right answer. That makes sense, right? If the solver would be perfect, basically, if it would give the right answer, there would be nothing to do. It would be pointless. But vice versa, or on the contrary, we want to set this up that it does something reasonable that's still fast, that just goes a bit in the right direction. So we want a solver that at least makes a step, kind of simplifies the other steps that follow, and gives us an initial kind of low fidelity guess about the solution. And then the network can take this. It doesn't need to start from zero, but it has some initial guess and can take this to refine it to an answer we want, potentially from a solver that is costly, that we don't want to run in that moment. Yeah, you can call the solver in the loop, but hybrid solvers, or they're actually by now different names for this in practice. And right, in this case, actually, this distinction between supervised and unsupervised breaks down a bit, because working with the solver, it actually typically uses data, but also generates data on the fly. We'll come back to that in the next weeks. I want to show one example here. So this is exactly the setup now. What you see here on the right side, your left side, is actually the basic solver. And this on the reference side is what we'd like to get out. I'm sure you can see clearly that there's a big difference between these two. In this case, it's actually just a matter of spatial resolution. So this one used a factor of 4 smaller spatial resolution and also temporal resolution, and that leads to this overly strong diffusion and smearing out of the dynamics. And then if you use exactly the solver, so I have this on the slides here. So this middle version still uses this source solver and runs, for every step of the solving process, runs a neural network on top of it to refine or correct the solution. Then you can get the answer shown here in the middle, and we can analyze this in more detail, but we can visually already see this preserves a lot more of the vortex shedding behavior and of the detail that this reference solve had. So this is the first example of a scenario where this makes sense. And then, of course, also The goal later on is that this runs faster than the reference, right? If we could just run the reference solver, we wouldn't gain much. But in practice, you can actually kind of trade in a bit of the generality. These are typically less general than the normal solvers for speed. So you can get this, if you're interested in a certain range of parameters or so, a certain range of behavior, you can get these answers quicker than with the general solve. And again, for typical application scenarios where you know to write, I'm interested in cars driving at human speeds, it might actually make sense to train a model for certain shapes, certain speed ranges that can then give you an answer faster in combination. Yeah, this is an overview of the topics we'll look at in the next, in the semester, in the next month. Basically going over supervised, loss terms, and these differential physics approaches. We also look at architectures like graph networks, time predictions, and also more recent topics, these diffusion models, I think are also worth covering in the context of physics simulations because they're quite neat. Reinforcement learning as kind of alternative or different viewpoint. And then also a bit of an outlook. I think these foundation models are also along the lines of pre-training huge models, an interesting future direction that at least we cannot cover in too much detail, and that would go beyond exercises, but as an outlook, it's nonetheless an interesting topic. Yeah, I also do want to mention right away, we cannot provide, don't want to provide an introduction to deep learning. We have other lectures for that, so I assume that that you all know, for example, the difference between autoencoders, UNet and ResNet architectures. Does anyone not know why we're here? Okay, I can recommend looking it up. Brave to raise your hand here. No, it's good to check. And typically we get these questions. I would encourage you to make sure you know the basics because we don't have time here to start from scratch here. Vice versa. Also, we do expect you to know some basics of numerical simulations. So, right, for example, typical finite differences. Does anyone not know the difference between central and forward-backward differences? Okay, also, I can recommend taking a look there. I think in both cases, it's not super complicated. So it is possible to learn this on the fly alongside the materials we're covering, but it's a bit of work. So I do want to mention this, that we expect you to know these topics. We basically want to focus on the combination. Yeah, also in terms of script, we have this website that in a way inspired the lecture, also that this lecture typically inspires in terms of content. So this is a good starting point. We will not provide a separate PDF script or so. Of course, the slides of what I'm showing here will be available, but slides and this website are the main reading resources. So also, if you haven't, that's a good starting point as to check out what will be following. Yes? So the question was whether the script or this book has the introduction for, say, the numerical simulation topic. It's very brief. I can. There should be important keywords and also typical examples, what we will cover and the complexity. So I can recommend to check especially the website for now to see whether this is on a level you feel comfortable with. Exactly. Yeah, no, this is actually a good point for questions because this is the end of the first part of the overview.